Okay, so welcome back to the third part of lecture 18. Um, we are going to now, specify the endogenous social effects in a spatial regression model. Until now, we have learned how to specify spatial dependence in a regression model through, spatial weights. So we are going to specify the regression model using the spatial weights and then, adapt Mansky's reflection problem onto the spatial, regression model. And then finally, as part of this lecture, we are going to provide the fixes for this purpose. So let's think about the the groundwater data that we have worked with till now. So let's say there is a spatial domain of interest as exhibited in front of your screen, and I am interested in explaining the groundwater depletion or groundwater depth at each location I in the domain of interest at any given point of time. So I have a model GI is equal to, I am going to use spatial weights to specify a spillover effect. So the point that I am trying to make is that all the values in its neighborhood is going to have a spillover effect on the groundwater levels at location I. Of course, the degree of spillovers can vary by the location of the neighbors. Okay. So all the dots in this sample will have contributed to the the level of groundwater at location I. So GI is written to be equal to rho, which is a coefficient of summation j equals 1 to n wij gj. Okay, j being the lag. Now we are going to use rho standardized weights, that is to say that wij tilde is wij over summation j wij. This is just to ensure that summation j w tilde ij will always be equal to 1, right. So this is going to be the case, plus some other factors, let us say beta 1. So I'm including the intercept beta 1 plus beta 2, sorry, let's just say beta 1 x1 I, beta 2 x2 I, and so on till beta k x k I plus ui. This is the regression model that we are used to. Okay. In the matrix form, we can write this as G rho Wg plus x beta, where x will be a k by 1, sorry, n by k, and k beta will be a k by 1 vector, plus u, which is a n by 1 vector, g is a n by 1 vector, and so is this one. That's it, right. So beta and rho are both model parameters. Now rho specifies the effect on location I due to its neighbors j. Now the reflection problem will suggest that first of all, what we are as an analyst, as an econometrician, as a statistician, as a researcher, as an analyst, you will be, what you are going to exhibit, what you are going to see is that data is exhibiting a pattern. That is to say that there are going to be clusters where groundwater depth will be very high. So the groundwater situation will be very bad. Let's say in one cluster it's an urban area, you have very low values of groundwater levels, and towards the east, in this direction, these groundwater levels are not so bad, they are fine. So what's happening obviously is that if I focus on any value in the north west cluster, I'm going to have, I'm seeing some kind of a spillover going onto this location I. What I don't know is that whether or not this location itself is also exhibiting a equal or stronger spillover on all its neighbors. So when we see average neighborhood effect, average neighborhood level groundwaters, right? So this is average, right? It's a weighted average. So WG is a weighted average. So it's average neighborhood groundwater level, and this is, individual well level groundwater situation, groundwater depth. Let's just call it depth in both situations. Okay, what we cannot ascertain by this, but just by specifying the model in the way we have, is that whether or not we can expect to have some effect of individual wells on all the wells in its neighborhood. This type of a intuitive understanding will also apply on housing prices. If I'm looking at a home or a house which has a high price and it's clustered with other high priced homes or houses, then we don't really know whether we are seeing the reflection of this house, how the price of this particular house on in terms of what's happening in the neighborhood, or this house itself is simply mirroring what's happening in its neighborhood. So who is affecting whom? Well, what happens generally in the real world is everybody is affecting everybody else. When we are talking about groundwater data, the groundwater, as we have looked at extensively, they are connected through aquifers. And so long as these aquifers beneath the ground are connected, the wells that we see, that we dig from the ground, if they go on into the same aquifer a cross section, then the levels that we observe are going to be definitely connected with each other. We can't just ascertain simply by specifying G equals rho WG as a single directional or unidirectional effect. There is circularity there which we cannot circumvent, right? And if you think about it, this WG, which is nothing but some kind of a weighted average, is an analog of expected value of y given x in Mansky's notation. Okay, so what we are looking at here is a endogenous social effects problem playing out in spatial regression models. Okay, and it's quite parallel. So then one can use Mansky's framework. So if you read Mansky's paper, Mansky provides constraints for parameters, some conditions for finding instruments in order to ensure that one can infer upon an effect of the neighborhood scale of outcome onto the individual outcome at every location in a spatial data set. Okay, now so now the next step is reconciling this spatial endogeneity. The first fix that I am presenting to you is coming from Luke Anselin. Luke Anselin is professor at of spatial econometrics, who is perhaps the father of spatial econometrics, who provided us this idea of spatial weights and weights matrices. Anselin says that weights matrix based spatial lag is not group mean. Remember, we looked at this idea of a moving window average, right? So moving average window, right? In this moving average, what we learned was the difference between a time series moving average window and a spatial moving average window is that WII is 0, that is to say the mean, the center point of this moving average window is not counted. So what Anselin is trying to say here mathematically is that the effect WG, which is the spatial lag defined using the weights matrix, is not equal to expectation y given x, right? Or let's say is not equal to expectation g given some x. Because you are not accounting, a location I is not her own neighbor. So every location is not their own neighbor. They are not accounted for while calculating this average, this group average. The individual is not counted when we are calculating the group average. So the problem of endogenous social effects arising due to this term does not exist, is what Anselin's argument is that the spatial lag regression is still identified even though there's troubling revelation due to the endogenous spatial effects or social effects. Okay. Now this argument has been critiqued by Gibbons and Overman in a highly cited paper called Mostly Pointless Spatial Econometrics, right. Now the argument that Gibbons and Overman are presenting is as follows. They are suggesting that causal inference, this idea of ceteris paribus or causal inference, is achieved by controlling for economic channels of effect, in the sense that unless you understand what is the channel of effect, you can't really ascertain a causal inference. You can't really get to the point what is this channel of coming from the left hand side to right hand side. Okay, and merely by using these geographic weights, which are only an index of who is near me in terms of my geography, in terms of my location, is not going to be sufficient in order to account for the economic channels of endogeneity, right. So if you are not able to account for the economic channels of endogeneity, then a weights matrix based argument that just because mathematically Wg is not equal to an expectation, a moving average expectation spatially, that doesn't suffice the fact that it is going to now identify causal inference, just because we have not quite done that, right. This is a very good paper. You must read this paper, but the point is that the Anselin's argument may not be sufficient, and there are in practice what we find is that people don't just stop at spatial lag models and say they are identified automatically, right. People do more than that. And one of the things that is done more is what is called as the instrumental variable approach. Here I have provided you an example paper which is using the instrumental variable approach in order to account for endogenous social effects in a spatial regression model. Okay, I am going to go over this idea of an instrumental variable approach in very briefly because of lack of time, but you can go back and study instrumental variables and instrumental variable approach for identifying endogenous effects in general, not just endogenous spatial effects, in Woolridge's book. Okay, so I am going to go over the instrumental variable approach very briefly as follows. So I am going to provide steps for the IV estimation approach. Step 1 is find regressors or variables, independent variables or covariates. Find regressors or independent variables or covariates that are likely correlated with the group effects but not correlated with the individual decision or outcome yi, right. So we want to find variables, we want to understand, we want to seek out some explanatory variables which will affect the group effects. So group effects are nothing but expectation y given x, something that is happening at the group level in a spatial neighborhood or in general in a peer network or wherever, right. We want regressors that are correlated with the group effects but not correlated with the individual decision, right. So let us say we call these variables Li's. Okay, so I'm using just the term Li just to sort of say this is one of the variable, one such variable, such that the correlation of Li with expectation of y given x being G, right? You can also call it G because it's a group effect. Then this will be non-zero, and the correlation of Li with individual effect is 0. That is to say that Li will impact Yi only through the group effect. Okay? So, we are after this regression Yi equals alpha plus beta expectation y given in G, right. So, y let me just clean this up a little bit, y equals this plus let us say eta z plus u, okay, and I am interested in beta as an analyst. So, I want to find a variable L which is correlated with expectation y given G, but uncorrelated with y. That is to say that the only way L will impact y is through G. Then I will go to my next step, step 2, and I will say run an auxiliary regression, also known as the first stage or the first stage regression. So, you will run this, estimate this regression model even before you are estimating your parent model or the model of interest, okay, the model of or a primary model, whichever name suits your is favorable in your opinion, right. So, the first stage model will be that I will go ahead and I will regress these average group effects, which is nothing but expectation y given G, on beta 0 or not beta, let us use a different notation, gamma 0 plus gamma 1 L plus epsilon. Okay. So, I am going to now regress these neighborhood level variables onto this instrument L. Okay. These are instrument. Okay. And then I am going to get my, obtain your gamma 0 hat and gamma 1 hat, and hence you are going to get your y bar hat, which is nothing but gamma 0 hat plus gamma 1 hat L, I. Okay. And then in step 3, we run this parent regression yi equals alpha plus beta, and we replace y bar g with y bar hat g. That is the predicted value in the first stage regression. This step 3 is called as the second stage regression. So, you are now conducting the same analysis in 2 stages. This is also called as the 2-stage least squares method, right. This is also called as aka 2SLS method. Remember, in this lecture, I am not doing a good job in terms of explaining what a 2-stage least squares method is. But you have all the tools to learn what it is, and I encourage you strongly to go back to the Woolridge's book and study what a 2-stage least squares method is. It is very general, it is very powerful, it is used a lot in econometrics research. Okay. Plus we have eta z plus u. Okay. Now, by using this, we will be able to identify beta, that is the endogenous social effect. So, we are able to reconcile the issue, the reflection problem that Mansky is raising, because we are not using y bar. So, I am just defining expectation y given G as y bar G, just to represent group level average of the outcome. Okay. So, let me just Okay, y given g, I am defining this as y bar g, just as a just to represent group level average. Okay. Now, the point that I am making here is that instead of using the raw group level data, we use it as a function of an auxiliary variable Li, which does not directly impact Yi. Okay, so we are trying to reroute the problem of endogenous social effects. We are trying to sort of get away with it. Because we have not used y bar g in its original form, we have also bypassed, or we have sort of, you know, uh, 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 you know, just avoided the issue of endogeneity, right? So I'm not going to call this an endogenous effect anymore. Beta is, of course, it's going to be the social effect that I'm after. So it's indeed an endogenous social effect. So, beta hat will represent that. Okay. So this is the second fix that I am proposing in this lecture. The third one comes from again a very good paper by William Brock and Stephen Durdorf, wherein they are suggesting that instead of using yi in the left hand side as a linear in their linear form, if we use a non-linear form of it, that is to say that if we were to model h of yi as the average level effect, then we will not have the endogenous social or reflection problem as provided by Mansky. It's mainly driven by the linearity. So I can have alpha plus u. You can read this paper. It's mainly for binary outcome variables, but it sort of also is a way to reconcile the endogeneity problem. Okay. So with this, we are coming to the close of to a close of lecture 18. But by lecture 18, we have now relaxed assumption A2 and assumption A3, and we have provided ways to estimate the models when these two classical assumptions of the regression model fail for the spatial data sets. Okay. So thank you very much for your attention. In the next lecture, coming lectures, we are going to spend more time with the spatial lag model, the spatial autoregressive cross-regressive model, the SLX model, the spatial error model, and we will study a bit of hypothesis testing with them, right? After that, we will move on to the hands-on exercise with ArcGIS and on RStudio. Okay, so thank you very much for your attention and see you in the next lecture.